Yes. Let's start.
Ready?
Yes, ready.
Okay, so Susagatam, Abhinandan, Namaskar. A very good morning, good afternoon, good evening, depending upon which part of world you are, but joining us live either on WebEx or on YouTube. A very hearty welcome to everyone from me, Anil Bharadwaj, for the first PRL Ka Amrit Vyakhyaan. Special and personal welcome to our chief guest, former Chairman ISRO and Secretary Department of Space, Dr. K. Radhakrishnan, and the distinguished speaker, Professor Harold Connolly, as well as Director VSSC, Dr. Sonda. I also personally welcome all the colleagues who have joined us live on this WebEx panel, as well as those who have joined us live on YouTube. PRL Ka Amrit Vyakhyaan is the start of celebration of PRL's 75 years. 75 years of history, of legacy, and which needs to be cherished and celebrated. Starting in the year 1947, by the father of Indian space program, Dr. Vikram Sarabhai, the research and development activities of PRL led to the formation of ISRO in 1969 and the Department of Space in 1972. Hence, PRL is aptly called as the cradle of space science in India. The Platinum Jubilee of PRL, or PRL at 75 Mahotsav, also coincides with India's 75 years of independence, an initiative by Government of India undertaken to celebrate it under the banner of Azadi Ka Amrit Mahotsav. Hence, it's a joint celebration of science and technology for India by PRL under the banner of PRL Ka Amrit Vyakhyaan. This Vyakhyaan will be delivered by eminent scientists, technocrats, engineers, as well as renowned personalities in the field of arts, literature, and social science, with a good representation from women celebrities. We plan to have this Vyakhyaan every Wednesday at 4 p.m., which will be live on YouTube channel of PRL and conducted through WebEx. The first Vyakhyaan of this 75 series of Vyakhyans is being held today, now, and who else other than Harold, suitable person for delivering the opening Vyakhyaan, or I should say the opening batsman. I don't know whether Harold is knows cricket or plays cricket or watch cricket, but cricket is the most popular sports in India. And Harold will be speaking on OSIRIS-REx sample return mission of NASA from the asteroid Bennu. Audience may be wondering, why Harold, why OSIRIS-REx mission, and why Bennu? The reason is simple and straight. PRL has about 5 decades of acclaimed history of working on samples in the labs. There are many legendaries who have been associated with this laboratory analysis of samples, including, I will just name a few of them: Professor Devendra Lal, Professor Narendra Bhandari, I think, who has joined us also live on this panel, Professor J.N. Goswami, and many of their children's and now grandchildren's. And the legacy continues. And one of them is sitting on this panel, and she is called Kuljit, or Professor Kuljit Maharaj. They have contributed significantly into the field and have worn a clothes. In addition to meteorites that fall on the planet Earth, including those falling within India, PRL has analyzed samples from Luna and Apollo missions. Luna 24 in particular, and Apollo 11, 12, and 17. And those were the days in 1970s. Currently, PRL hosts the most sophisticated instrument called NanoSense, the only one in India, which has the capability of analyzing samples of nanosize. NanoSense stands for Nanosecondary Ion Mass Spectrometry. Coming to sample return missions in the recent years, PRL's NanoSense has been used to study the samples from Japanese Hayabusa 1 mission, which was a mission to asteroid Itokawa, and plans to have the samples from Ryugu asteroid, that is from Japanese second mission called Hayabusa 2. And now planning or aiming for a bit of probably a gram or so from Bennu, from NASA OSIRIS-REx mission, when it returns back the sample to Earth in the year 2023. So our today's distinguished speaker, Harold, will be providing a great view, or I should say overview, of this mission of NASA. And we are really delighted that he has accepted our invitation and is delivering the first PRL ka Amrut Vyakhyaan. So with this, I once again welcome everyone to this mega Utsav, the Mahotsav, PRL ka Amrut Vyakhyaan. And I thank you all for joining us live on YouTube as well as on WebEx and celebrating PRL at 75. Dhanyavad. Thank you. Now it is my pleasure duty to introduce the chief guest of today's event, Dr. K. Radhakrishnan, before formally calling him. Of course, he doesn't need any introduction, but for the sake of the young audience who is there, including the school children and college students, Professor Radhakrishnan, as we all know, has been the chairman of ISRO, Secretary Department of Space, and chairman of Space Commission for 5 years during the period November 29 to December 2014. Before that, he has held many responsible positions within ISRO, including Director of ESSC, Director of NRSC, as well as his small stint of 5 years as a Director of Inquiries. He is very well known in his own areas, and I'm not going to detail on that, except to tell you that he is a fellow of Indian National Academy of Engineering, as well as of National Academy of Sciences, and many others, including academician of International Academy of Astronautics. Even at this age, he is having several responsibilities. A couple of them is like chairman of Board of Governors of IIT Kanpur and chairman of Standing Committee of IIT Council, beside, of course, the honorary distinguished advisor of Department of Space. He is just 1 year short of 75 when India is celebrating 75 years of independence, and PRL is celebrating 75 years of its existence. He has contributed significantly to the missions of India, including the Chandrayaan-1, and of course, more importantly, the Mars Orbiter mission, that is the MOM or the Mangalyaan, which was launched in November 2013, arriving on Mars on 24th of September 2014 with a lifetime of 6 months. But after around 7 years of its functioning, MOM is still active, alive, working around Mars. So that is the tribute to Professor Radhakrishnan. So with these few words, I will now request Professor Radhakrishnan to inaugurate this function, and which we call as PRL Kamrit Mahotsav. And may I request Bhushit to just put on the curtain raiser of inauguration. And I will request our beloved Radhakrishnan ji to say a few words of opening, and after that he will really deliver the inaugural address. So over to you, sir.
Thank you, distinguished director of PRL and my beloved colleague, Dr. Anil Bharadwaj, esteemed members of the PRL fraternity, the erudite guest speaker, Professor Harold Connolly, and my beloved colleague and the current director of Vikram Sarabhai Space Center, Sri Somnath, who has joined us for this session. I am proudly privileged to inaugurate PRL Ka Amrut Vyakhyaan as an online series of weekly colloquia organized as part of the Platinum Jubilee celebrations of PRL.
Thank you, sir. So now may I request you to say the inaugural address.
My young friends who are watching this program and who are going to watch this program, who are going to benefit from this series of online lectures organized in this year, my greetings. And I want to say that the PRL, founded by Dr. Vikram Sarabhai in 1947, has evolved as a premier national institution of international acclaim. And also, PRL has been a preferred destination for some of the best brains of this country who have been working in the frontier areas of physics. Let me also take this opportunity to salute the stalwarts of PRL for lending their might and life to build this institution to global glory. Notably, as Dr. Anil told, India's space program and ISRO were nucleated and nurtured by PRL. And I cherish my long association with PRL in diverse roles from the early 1980s, and particularly during the 5 years of leading space program. And I also want to say that 50 years ago, as I started my career in ISRO at Tumba, we were all part and parcel of PRL. And obviously, I feel at home and elated to be part of this celebration today. PRL has played a seminal role for India's lunar mission Chandrayaan, especially to conceive lunar science, build scientific instruments, and further the national scientific talent pool for planetary exploration. And I'm extremely happy that Professor Bhandari is able to join us today. And another person whom I would like to recognize is Professor J.N. Goswami, former director of PRL. And also, let us recall the spirit of embarking on India's Mars mission with the interdisciplinary feasibility study team set up exactly 11 years ago. And we saw the fruition of that in year 2014. And I'm also happy to see Dr. Anil Bharadwaj, who has been one of the instrument builders for this MOM program. And I'm also extremely happy on this occasion, Somnath being there, because he has given us the might to put all these missions into the orbit. through the PSLV, which he nurtured from the beginning of his career. And I wish the current generation to raise PRL as a friend ranker institution in big science, quote unquote. Look at a big problem that the universe or the humanity are going to be concerned about and look for a solution which can come with the synergy that you have with the mighty ISRO, with whom you have a symbiotic link still. And space technology helps us to know more about humanity, and that is your field of activity. To serve the humanity, that is ISRO's activity, and to raise the level of science and technology that are crucial for the growth and sustainable development of this country. This is the joint goal of all of us in this field of space. The world is now in the dawn of a new space age, especially with the emergence of the new space protagonists, and also a commercial space sector that contributes about 75% of the global space economy. We are also in a multipolar world where joint space missions have become the order of the day. Megatropics, SARAL, the NASA, ISRO, radar project. Now, these are all examples of how people could leverage on each other's experience and expertise. And space science, space exploration are areas where in abundance you get partners to do. And the mere presence of the speaker today tells there is a lot for the humanity to look at the universe. And there are 17 national space agencies today, and delightfully, some of the new entrants are engaged in the frontiers of space exploration. Also, the technology that has been advancing exponentially help us to aim high in space exploration. Exploitation of celestial resources, that is the talk today. Space applications and high-tech space enterprise. Development of scientific instruments, I would like to underscore. And if you want to do cutting-edge scientific research, if you want to do first-class science, you must be able to conceive and build your own scientific instruments. The space robotics, space habitat, versatile spacecraft systems and powerful rockets, the ability to navigate the spacecraft and the rendezvous in the solar system, mining of celestial resources, along with downstream processing at Earth. Now, these are some of the challenges which the current generation of PRL and the space community at large are going to face, and I'm sure they will come up with solutions. In this context, the opening talk of the series by Professor Harold is the most relevant thing. The most recent asteroid mission he is going to talk about. And that should set the tune for the futuristic evolution of a vibrant PRL that is in your hands. And with this again, I'm delighted. I thank you for this kind invitation, and I would like to listen to the talk and get excited about it. Thank you very much.
Thank you. Thank you, Padma Vibhushan, Dr. K. Radhakrishnan, for illuminating talk, showing the connections between ISRO and PRL, your own connection to PRL, and how PRL should conduct in the future, particularly in the changing scenarios. We really thank you all, as well as Dr. Radhakrishnan, for being live with us once again. And may I now request Dr. Kuljit Marhas, Kuljit, to take over from now on and first introduce the speaker and then ask and request the speaker to deliver the PRL ka Amrut Vyakhyaan.
Thank you, Professor. Thanks. So it's a great pleasure to introduce Professor Harold Connolly, especially because I have been very amazed and impressed by his energy and enthusiasm in planetary science. And I have been really following his work for last 20 years now. Professor Harold Connolly is a highly distinguished, accomplished planetary scientist. He is a co-investigator with the title of the Mission Sample Scientist of NASA's OSIRIS-REx, a new frontiers program of NASA that shall return about 60 grams of primitive sample from Nightingale site of a pristine carbonaceous chondrite named Bennu. He also serves as the co-investigator of the Japan Aerospace Exploration Agency Hayabusa 2 mission, which has brought back sample from the asteroid Ryugu on 5th September 2020. Professor Harold completed his master's and PhD in geological sciences from New Jersey under the mentorship of Professor Roger Hivens. His seminal work on petrology and formation history of chondrules led him to several distinguished research associate and scientist positions at institutes like California Institute of Technology, American Museum of History, Washington, D.C., Lunar Planetary Science Laboratory, etc., before he chose to settle as assistant professor position in Department of Physical Science at Community College in New York. He rose in rank with several academic and administrative responsibilities to start afresh as the founding chair and professor at Rowan University in New Jersey, USA. In his distinguished research career, he has published around 100 research papers, including more than a dozen in high impact factor journals like Science and Nature, along with hundreds of conference proceedings and abstracts. He has also edited and authored more than 10 volumes of books. It is very interesting to note that he has an asteroid 6761 to his name. And with his colleague, he has also co-discovered a new mineral named crotite. He has been awarded more than a few dozen multi-million research grants and is very worthy recipient of several fellowship and awards, including Antarctic Service Medal, NASA Group Achievement Award, and visiting professorship at University of Hokkaido and University of Tokyo, where he is currently analyzing Hayabusa 2 samples. He is a frequent visitor to India owing to his belief in Buddhism apart from his scientific interests. He also enjoys cooking, classical music, surfing, and sharing conversation with his friends and family. He is a very great science communicator, a very gentle, humble, and kind human being. It is with great honor, delight, and respect that I invite Professor Connolly to deliver today's inaugural PRL Ka Amrut Vyakhyaan. Professor Harold Connolly, can you please join?
Thank you very much. I am humbled by the introduction, truly humbled to be with so many distinguished colleagues here today. And I want to thank everyone for the series, for inviting me, my friend and colleague, Professor Marhaus, for inviting me, Professor Nadidas and the committee for inviting me, the director and the dean. And I'm really excited to be talking to you about the OSIRIS-REx mission. I'm in Tokyo right now, where it's, what time is it? 8 o'clock at night. And I've been here since the 23rd of June, and it's been an interesting experience. So I'm going to share my talk. The talk will have a flow to it, give you a little history of the OSIRIS-REx mission, moving into the findings, and finally ending with the current status and what we expect we will be doing in a very near future. Let me share my slides with you. Sorry, I'm working on 2 screens here, so it's not quite professor proof. Okay. Can you see my slides appropriately?
Yes, yes, we can.
Excellent, thank you. So the title of the talk is, as you can see, OSIRIS-REx sample science and the geologic context of return sample from active asteroid Bennu. As Professor Marhas informed you, I am a geologist by training, a sample scientist, meteorites, and asteroid geology I've worked on for my entire career. And I'm the mission sample scientist, which means it is the title that encompasses everything to do with anything to do with the return sample, from its analysis when it comes back on the 23rd of September of 2023, 24th of September 2023, to the origin of the sample. How did it get where it is and was collected from? What's the entire history of the asteroid that generated the sample? So it's a diverse title that has literally encompasses everything to do with the molecular cloud of the solar system formation through to the current threatening state, if you will, of the asteroid, which is an Earth crosser. So if you're going to want to know something complicated in the audience about navigation, I might not be able to answer that question for you, but I will try. And I want to say happy 75th anniversary to the PRL. As was mentioned earlier, you have a very long lineage of outstanding contributions in the field of sample science, extraterrestrial samples. And I had the great pleasure of attending a conference, Terrestrial Planets Evolution Through Time, in 2008. And here are some images of our colleagues, John Watson and Goswami. And this is actually Sasha Krot that, as you heard, the mineral crotite was named after, which was actually found initially by one of my undergraduate students. And of course, I think the audience, everybody knows this individual. OSIRIS.
Harold, I'm sorry, but I don't see your slides moving.
Nothing moving? Moving for me.
It's just the first slide for me.
Okay. You have some sort of problem then? I don't know. You see now?
Still the first slide.
Still the same slide?
Yeah.
Okay.
Maybe you can come out from full view and then again go back.
Yeah, let me try. Thank you. I'm sorry. How about now?
First slide.
Still the
Yeah.
first?
Yeah. There you go.
Yep.
Okay,
Perfect.
I'm sorry, everyone. This worked earlier today.
We're able to see the second slide.
Now you see the second slide?
Right.
Yes.
Okay, maybe some lag now for some reason. I don't know why. Okay, so there's the second slide. So I'm sorry, that's the happy 75th anniversary to the PRL. These are some images I took back in 2008 of our colleagues and of the city of Ahmedabad, which I enjoyed very much. How about now? Do you see a slides? Different slide?
Yes.
Yes, Harold.
Okay, thank you. So OSIRIS-REx. So as was told you moments ago, OSIRIS-REx is NASA's New Frontiers 3 asteroid sample return mission. That's one of the three major programs that NASA has for space exploration. The main objective of the mission is to return a minimum of 60 grams of pristine asteroid regolith to investigate the history of asteroid Bennu through sample analysis. The name is an acronym, which NASA loves to have these kinds of complex names. O stands for origins. The S and I stands for spectral interpretation. The R stands for, it should be I here, my bad, resource identification, security, and regolith explorer. Now, I'll give you the conclusion, as we say, punchline already is that yeah, we did collect more than 60 grams of sample, but we'll get to that. The OSIRIS-REx asteroid sample return mission, and we're going to come back to the importance of a sample return mission as opposed to any other kind of mission that is or has flown, launched at 7:05 p.m. on the 8th of September 2016 from the Kennedy Space Center. This is the United Launch Alliance official image of the rocket going up, which was incredibly impressive. And these two images here, you are seeing my slide, correct, of the launch images? Yes. These two slides here were taken by my colleague and friend Jackie Flaherty at the American Museum of Natural History's father, who was on a non-commercial airline and was flying by the launch when it happened. So you can actually see the launch trajectory right there. Now, we had planned the whole mission, and this is an animation from 2013, to go down to what was indicated as going to be a smooth surface asteroid with our collector, and this is what our collector looks like in animation, and I'll show you images later on of the actual unit, and collect gently on this sea of fine-grained centimeter to millimeter sized dust, what we call regolith beds on the surface of the asteroid. So our whole engineering and collection campaign was designed for what we had the information at the time of what the asteroid surface was going to be like. Well, when we arrived at the asteroid in December of 2018, it looked nothing like we had thought it was going to look. So we all screamed in our heads. The surface of the asteroid, like the surface of asteroid Ryugu, which also surprised everyone, is littered with boulders, completely littered everywhere. And keep your eye on this rock here, which is known as Ben, and we're going to see the scale in a moment to give the audience some feel for the actual size of Bennu and its rocks. But we did not expect this, okay? Here is for scale, Tokyo Sky Tree with the asteroid image put next to it, roughly to scale. This is the boulder Ben, put to scale with this 11-story building down here. So this is no small boulder. This is huge. Why is it kind of a shock and scream in the head? Because both missions, in this case, designed not to have to deal with this kind of hazard of these large boulders through their engineering. So we had to, as you'll see, rethink many of our initial concepts that we had worked towards. But it's beautiful. It's totally beautiful, okay? This is the same image here, flattened to a mosaic. So we can easily look at it as if it's a map. And the pixel size is pixel size is 1 pixel is 0.33 meters per pixel. And again, here's your Ben for scale, okay? And you notice right away, there's a huge set of impact craters that goes across the equator right here. And if we zoom in a little bit, you begin to see all kinds of geomorphological features that were a surprise. People like to ask me, what did you expect? And I tell them, well, we didn't know what to expect, but we didn't expect this. So that's the way it works in space exploration. Here is an impact crater, one of my favorites, with a stone, roughly a boulder, roughly 12 o'clock, bigger than a bus, which is really bright. Other boulders, which are quite dark. In actuality, the asteroid itself is as dark as a piece of coal in space. It only has about a 4% albedo, 3.8. So you're looking at very subtle changes in the grayscales reflecting in the actual light that comes back to the camera system, which was designed and built at the University of Arizona, known as the OCAM system. Closer up, you can even see that there are impact craters inside of impact craters, attesting to a long history of reworking of the surface. Large areas where boulders have slumped down and mass wasting is going on. And you can see very clearly here in this picture, in this image, the difference in grayscale corresponds to obviously differences in black and white color of the image, which relates directly to differences in composition and texture. There are differences in textures in the boulders as well. This was a wonderful surprise. Very, very pleased. However, we expected to have large areas of centimeter to millimeter sized particles. And as you can see by these few images I'm showing you, it's not there. I keep one of these mosaics at a higher resolution on my desktop so that when I'm sitting through more and more telecons that happen, especially since pandemic, that often go from 8 in the morning until 6 at night, sometimes to discuss something you've already discussed in academia and already agreed upon and are discussing again, I look at the images more and more and I find things I didn't see earlier, and it's incredible. But don't get distracted from the prize, because looking at the geology of the surface is a wonderful thing, but the point of doing it is to stick to our prize. And what is the prize? Well, the prize is that it is a sample return mission. And we had to train our minds at the time not to get too carried away with doing science during the operation phase of the asteroid, but supporting the sample site selection and the collection of the sample. And this is colleague Akira Tsujiyama, at the time from Kyoto University, who was a lead of sample analysis for Hayabusa. And these are 3D printings of every grain that was studied in the analysis process for Hayabusa. And you can see I'm a remote sensor because you can see me in the background here in the mirror, okay? So some highlights from the geology with words to give you the serious results that we discovered in our exploration of asteroid Bennu. The asteroid, as you already know, appears compositionally diverse. There are a diversity of boulders, both with respect to their albedos or colors, or grayscales, and their textures, which was not what we expected. The asteroid itself is a rubble pile or a loose accumulation of material held together by a very small gravitational force and tensile forces that hold it together, okay? This was good. We predicted that, and most of these little asteroids are what we call rubble piles. They're not one solid rock. The equatorial ridge right here, which about 20%, 15 to 20% of small asteroids have, we predicted that from the radar images before we arrived and we found it. It has abundant craters, okay, up to the order of 1,500 plus craters, which is a huge surprise on a small asteroid. Okay, very large boulders, as you'll see in a moment. We'll go through the size range, unconsolidated surface. There's a very low density, which means it has a very high macro porosity, okay? And it has very low slopes. Bennu contains over 3,000 boulders between 1 and 58 meters. Okay, the largest of these boulders, Ben, and this one right here, are too large to have been ejected from any crater, impact crater on the surface of the asteroid. So they are actually remains. The hypothesis is they are remains of the previous generation of this asteroid, because the asteroids that we look at, such as Bennu and Ryugu, have been through multiple generations of reshaping and changing, okay? And then I'm covering up something here, sorry. And then boulders greater than 30 meters are probably the remnants of Bennu's parent body, as I just said. Another surprise for both asteroids, but focusing on Bennu here, was the fact that there are breccias all over the asteroid. Large breccias. You see the scale bar here. This was a wonderful, delightful surprise. We shouldn't be surprised when you think about the meteorites we have in our collection, because a large percentage of meteorites are actually breccias. However, we don't see them the size of boulders. We see them hand sample size. So this was really wonderful and encouraging. We discovered very early on during the approach phase, actually in December of 18, we did an experiment where we put our thermal spectrometer on and visible spectrometer on as a bulk analysis process of the asteroid. They weren't designed to be that particular kind of instrument. They have to actually get closer and finer detail to really analyze. Nevertheless, we had a very pronounced 2.74 micron feature, which immediately told us the asteroid was rich in hydrated phases or clay minerals, which is exactly what we had predicted and hoped for in our early characterization of the asteroid. So this was wonderful. It had been predicted to be similar to CI and CM chondrites, for those in the know, and it sure seems to be like that, which is exactly what Ryugu also was predicted to be. And we're going to learn about that in the next few months. Okay. Bennu has a carbonate feature. It has carbonates, and it has carbonate veins. This was wonderful discovery, an incredible discovery. We find, for those that don't know, we find carbonates in CM and CI meteorites, and generally in small quantities or in veins. We know that they're there, but here we have veins that are order of centimeters big. And we wouldn't even think, if we found a meteorite that was actually all carbonate, that it would be from outer space, because we naturally wouldn't think about that. So this was an exciting discovery. Okay. We also have magnetite and carbon phases, organic, detected on the surface of asteroid Bennu. So very exciting. Part of the main mission of OSIRIS-REx and of Hayabusa 2 is to bring back volatile-rich samples to help us study the earliest time periods of the solar system, including prebiotic compounds. Because once a meteorite lands on Earth, it begins to change right away, instantly. And then early on, looking at images of asteroid Bennu, we noticed there are rocks on top of rocks. Okay, here's the scale bar, and some of them are angular. We thought that's rather odd. And then here's more, and we thought that's strange. And we thought to ourselves and laughed, what goes up must come down. Well, before we arrived at the asteroid, we had gone through a campaign of looking for comet-like activity from the asteroid, because one of the major hypotheses for the origin of these B-type asteroids, spectral type asteroids, B, is that they're extinct comets. Well, we didn't see anything. And then all of a sudden, Carl Hergenrother, the working group lead for the astronomy working group, was processing some navigational camera images, and this is the way it works in exploration, and accidentally discovered that the so-called stars that the camera was looking at weren't stars. They were actually ejection material from the surface of the asteroid. Now, the ejection was not accompanied by your typical comet-like activity with a lot of volatiles or gas. If there is any small quantity of volatiles or gas, we don't have the resolution to pick it up. But we noticed more and more of these events occurring over time, and some of them were rather extreme, lots of particles, and some were like popcorn events, what I call popcorn events. We would notice 4, 5, or 6 little popping, and we would follow these rocks around the asteroid for 2 or 3 days, and then they would disappear. Presumably, they fell back down. So this was quite a surprise to have an active asteroid, because we cannot see this from Earth-based or even orbital-based telescopes. It's not possible. So now we had a surface that was active, and the first thing we had to do was stop screaming in our head, because we were worried about the safety of the spacecraft, is really go into detail and explore these particles. So we determined that they were not a threat to the spacecraft, so we could continue with our main mission, which is to collect a sample. We also discovered that there are a small number of boulders on the surface of the asteroid that are extremely bright, 17 to 20% albedo, that just didn't fit the normal picture of what we were seeing. And the conclusion is, the hypothesis is that these are actually basaltic material that come from different type of asteroid that impacted onto the surface of Bennu. So it really is preserving a sort of trash can, like tourmaline being a trash can mineral, which almost anything can fit into its structure. In this case, these small asteroids are picking up lots and lots of material in the solar system. This is our collector, TAGSAM, Touch and Go Sample Acquisition Mechanism. This is a 3-meter arm. Right here is in the high bay area of the Lockheed Martin facility, which is one of our corporate partners that built our spacecraft, which did an outstanding job. And it's a clean room facility because it's a sample return mission, so we don't want to contaminate any part of the sample or any part of the spacecraft. This is the actual collector head, as you'll see more images in a moment, where the sample gets collected into. And here are 2 of the 3 nitrogen bottles that were used to fire nitrogen to the surface of the asteroid once this touches, to fluidize the regolith bed, to basically reverse vacuum it into our reverse Hoover TAGSAM. This is what the collection head looks like. It's 2 collectors in one. There's a bulk collector here that can collect up to 2 kilograms of material. And then there are these small 24 of these small contact pads on the surface which are made of a kind of steel wool, which are designed to collect the smallest grains that sit on the surface of the asteroid, because there are many scientists that want to study the space weathering effects of airless bodies. And we learned this from Hayabusa 1 because of the work that was done on the lunar soils that showed us that radiation bombardment over time damages grains on the surface of airless bodies. So this was a really incredible lessons learned from both Luna and Apollo missions, and of course, Hayabusa. This is a bit of redacted material I'm not allowed to show you because Lockheed Martin didn't want it shown. Here is an animation of how our collector works. Once it touches two of the four sensors, fire to 2 of the 4 sensors. Once it touches, the gas fires, and you fluidize the bed, collecting the 2 centimeter or less particles into the main collector. Okay. Again, don't forget, training the mind. The results from the science campaign around Bennu are totally fascinating, but the mission's goal is to collect and return a sample of the asteroid. Okay. The major point of the asteroid operation phase was to find a suitable site for sample collection. And the question is, how were we going to, and how did we choose our candidate sample site? This is very important. We had originally in mind several key variables and factors that fed into those variables. There are 4 maps that needed to be produced in order to find a suitable site to collect sample on the surface of Bennu. We had to be able to deliver that to the spacecraft to that area. It had to be safe, not only safe going down to the surface, but safe backing out of the surface, going back into orbit, because the actual going in to the surface and coming out of the surface plane may not be identical. There may be differences. We had to have material that we could sample, so 2 centimeters or less, and we had to find a site that had a high science value, which for us meant a lot of volatile rich material. Well, the original idea was we designed our collector and navigation to go to an area of a 25-meter radius. Well, that was now impossible. Once we saw the asteroid surface and screamed in our heads, we had to change things. And as it turned out, the navigation crew was able to refine their navigation more and more and more, as engineers and physicists often do, to the point where we were able to get down to a 5-meter radius from 25 that we knew confidently we could collect from. Turned out to be a 1.5 meter in the end. Okay, we had to keep good communication with safety, and we wanted to make sure temperature was also not too hot in certain areas and certain times of the asteroid's day, which rotates around its asteroid at a little over 4 hours. That was not a problem, but the big boulders were a problem. So we had to make sure we could fly in and fly out of the area. Sampleability became a problem because we were using thermal inertia, the thermal properties of the material as measured before we arrived, and then supposedly at the asteroid operation phase to give us a proxy for centimeter to millimeter sized particles. But there's something we don't understand about thermal inertia on asteroid surfaces, because the same problem happened with Ryugu. We have the analysis of 350 plus for the thermal inertia, but we do not have ponds of regolith floating on, or laying on the surface of it. So we had to actually have a whole campaign to find particles we could collect. And finally, we decided anywhere on the asteroid is going to be valuable to collect. So we didn't have to worry about science value too much anymore. This is a movie I'm going to show you, designed and made by the Canadian Space Agency in collaboration with NASA, of our laser altimeter. The OSIRIS-REx laser altimeter, or OLA, is a laser altimeter that supported the sample collection and science objectives of the mission. And what you're looking at is a rendering of the actual data from the laser pulses going down and coming back again over the surface of the asteroid. Several billion data points of 6 centimeters footprint. And this will show you how we brought down from June of 19 to September of 19, the number of sites, potential collection sites, down to 4. It has some music that you may or may not hear. We had trouble with that earlier. Again, you're looking at the actual laser return data points. These two sites are on equatorial ridge that were candidate sites. This is in the northern hemisphere. Turned out to be our site, as we'll see in a moment. And then one in the southern hemisphere, all of which are essentially impacted. And this is the first time a small planetary body, such as an asteroid in this case, has been completely mapped with a laser altimeter system. Now, we had to narrow it down even further. And to do that, we had to change some of our plan and go down closer and closer to the surface, to the point where we get resolutions on the order of about 5 millimeters per pixel, which is incredible imaging. And we picked Nightingale and as our primary site and Osprey as our backup site to collect sample. These are both in impact craters, and the hypothesis and the reason why it's important is because the impact craters are excavating material from underneath the surface. So the material below, we hypothesize, will be fresher than that material right on the surface. Thus, hopefully, more volatile rich. This is actual image of Nightingale with an animation, or sorry, an illustration of the spacecraft to relative scale, as well as a car park with a car in it, so you can see how big the site actually is. It's not very big. Okay. Now, on the 20th of October, 2020, not 21, my mistake. I'm sorry for the typo. We collected sample. These are the actual images from the spacecraft of the collection process. You can see part of these in the media, but what I'm showing you is actually the relatively unprocessed original movie. Now the actual collector is moving backwards. The spacecraft has fired its thrusters and is moving backwards. And as you can see, there's dust everywhere. Again, the punchline or the important point is we penetrated the surface of the asteroid 48 centimeters and never expected to do that. That is incredible. Okay. So, in 20th of October, we were very, very happy, and the whole world, newspapers, articles everywhere were picking up our collection success, and it was quite impressive. Even the classical music station from New York, what I listened to, had a little blurb on it about the success. And these are images taken in 2018 in November, after we actually removed the collecting device, a taxiing device, from its kept area in the spacecraft. We imaged it to see the clear, beautiful images in space. And you can see the sunlight coming through it. And these images were also taken because we were planning to do two things once we collect the sample to prove to ourselves, to gain confidence that we had at least 60 grams of regolith, so we would not have to go back down to the surface and collect more. We needed 60 grams. The first one was to take images like this using our SamCam camera to look and see if there was sample inside the collector. This is the bulk collecting area in here, which actually has a mylar flap over it, okay? And these are those contact pads that we discussed that collect material of fine-grained nature, millimeter size, right on the surface. And then after we did that experiment, we were then going to put out the arm again and rotate the whole spacecraft to do a moment of inertia to figure out the mass. Well, we then downloaded these pictures. They came in between 2 and 4 in the morning that night after taking them. And the first thing we all saw, many of us woke up early, I did, to look at these images, something we never expected. All that scattered light. All that scattered light is sample actually escaping from the collector head. We never expected this. This was a surprise. We thought maybe some would be on the surface as you backed out. But then, of course, the newspaper headlines the next day, asteroid sample spills back into space and that jammed NASA spacecraft, and how NASA scrambled to save OSIRIS-REx from leaky disaster. Well, wasn't that bad, okay? This is the news media. What had happened was we collected samples so well, most likely because of pushing into the surface 48 centimeters. When we fired the nitrogen, we had already been pushing sample into the collector in a way we never experienced in thousands of tests we did. These are actually, if you can see my cursor, these are actually large grains right here, 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 down in here, okay, that are actually stuck in the orifice, keeping the mylar flap open so that material is leaking out. Every time we move the arm, we were losing several milligrams of sample. So we had to make a decision with NASA headquarters to change our plans and not do the moment of inertia and spin the spacecraft because we were afraid of losing too much sample. This is, by the way, estimated to be 3 centimeters big. It's lovely. So 2 centimeters in one direction, 3 centimeters in another. That's a boulder for us meteoriticists, okay? This is an image showing you the actual contact pads with little grains stuck in them. So we know we also collected there, and this is dust that's all inside the collector. The dust is everywhere. We definitely have sample, no question about it. So the decision was made to stow the sample. These are the actual images from the spacecraft taken in space of the sample being stowed. You can see particles being liberated as it's stowing. Look, see? Particles still escaping as we clamp the head into the sample return capsule, which is right here. And these are the clamps. The next thing we had to do, engineering marvel, is fire a small pyrotechnic to remove the arm, and the TAGSAM head is captured in the sample return capsule. And then we shut the lid. Done. Brilliant. These are before and after pictures taken when we went back in April of this year to look at the sample site. This is before collecting, after collection. As you can see, we definitely disturbed the surface, and you can see a small crater in the surface where we collected. On the 10th of May of this year, we performed our departure maneuver, where we left the vicinity of asteroid Bennu and said goodbye to it, and that too was flawless. And I will brag about both missions and engineering teams, combination of working with scientists and engineers together, has been flawless navigation, flawless, just everything has been flawless. And this is a little unusual, both of these missions, because the scientists were quite often telling the engineers, slow down, wait a minute. Usually it's the other way around. That's space missions, okay? So the sample then will come back to the US in the Utah desert, landing gently with parachutes onto the surface, and will then be put in nitrogen, sealed up, and flown with a military aircraft to Ellington Air Force Base in Houston, Texas, where we'll arrive at the Johnson Space Center in a brand new laboratory being built for the new curation facility, and a catalog of sample will be created within 6 months, and the analysis team will start immediately analyzing sample within the first day, and we are funded for 2 years, and it's an international team that continues to grow of researchers around the world who are involved in the analysis. And it's my privy to conduct the entire analysis process when the sample returns globally. And we have a whole team of not just analysts, but also of engineers and software engineers who are working with us to develop things right down to a tracking app for your phone, where we can actually track a sample with your phone and communicate to me and to other people about what's going on with your sample. So it's really been a lot of fun. I'm doing things I never thought I would do with respect to engineering in my life, and it's been amazing. And again, happy birthday to the PRL. I want to thank you very much for the invitation, and it's been a great pleasure to share our mission with you to date. And I'm sorry I can't be there in person. I would love to be there in person, but that's the way our world is right now.
Thank you, Harold, for such a very informative and impressive talk. And I'm sure you will be flooded with some questions. So give me a minute or two to check out the questions that we have in the chat box.
No, that's fine. No problem, as we say. Our director has a question?
Yes, I do.
Please.
Such a wonderful talk, really enjoying and looking at the whole mission, and it was a journey as if we are watching it live happening. So that was really very nice.
Thank you.
My question is related to this curve which you showed and talking about a dip coming somewhere around 2.7 to 2.8 micron.
Yeah.
And does that indicate the presence of OH and H2O on asteroid?
Yeah, that's a great question. Certainly a hydroxyl, probably also the band depth, probably trapped water as well in between the sheets. The same sort of data set from Hayabusa 2 shows a very limited band depth here, very small. So it seems to be some difference in the chemistry from the spectroscopy between the two asteroids. And that's actually that's a really good, insightful question, because that's one of the potential mechanisms that's causing the asteroid to be active for the actual particle ejection events. It may be that trapped water in the phyllosilicates is actually basically heating up and exploding, and that's causing the non-comet-like activity. That's one of the hypotheses we put in the paper, because we don't really understand how the dehydration of phyllosilicates occurs in space in zero pressure. So it's a great question.
Mm-hmm. Why I asked you this question was because in the case of moon, we have seen the discovery of water happening because of this dip, which is seen somewhere around 2.8 to 3 micron, which is directly linked to OH, H2O, and this is something very similar to what we are seeing in the case of asteroids.
Yes, right.
So, there are a few questions. One is from Dujesh Ray, asking if Bennu is hazardous in the sense that there is a chance of collision with Earth in near future.
Yes, there is actually. So part of the built into the name OSIRIS-REx is security. So one of the reasons we want to Bennu is because it's a potentially hazardous asteroid, and it has a 1 in 2700 chance of impacting on the Earth in the 23rd century. And it's one of the major problems about predicting asteroid movement is they actually move because they're getting heated by the sun, and that radiation, that energy is radiating off in what's called the Yarkovsky effect. And the equation requires the composition, and we don't know the composition of asteroids very well. So that's one of the reasons to bring back samples. Yeah.
But in a sense, it is reducing its mass, yeah? So in 23rd century, probably we are left with nothing.
That's true too. That's a very good point. Yeah.
Yeah.
The predictions of impact, statistical predictions, are actually what's referred to as a keyhole prediction. So it has to go through a certain area near the Earth where the gravitational pull could be sufficient to pull it. So it's not a direct linear sort of correlation. It's like predicting the weather in the next couple of days. It's not a linear correlation, as we all know.
Right.
Yeah. Yeah.
So there's another question asking surface temperature of the asteroid. I mean, this particular asteroid.
Yeah, so I think that I'd have to double check. I've got so many numbers in my head now. The maximum temperature, I think, is around 385 K.
So you do expect the water to blast off some material then, right?
Yeah, correct.
So there's another question which asks, does the sample get contaminated when the pyro is burning for detaching the arm?
Great question. So there are two campaigns we had during the building of the spacecraft. One is an engineering requirement, and is contamination control, where it dictates what kind of materials you can use in building the spacecraft for contamination purposes. But because we know we're human, we know mistakes will happen. And typically you won't know what the mistake is until after the sample comes home, as we saw with Hayabusa. So we have lessons learned from Hayabusa. So we also created a science campaign of contamination knowledge to monitor the entire process. And that includes also archiving and analyzing the biofuel that was used for the thrusters as well. So we have that curated, already analyzed and already curated from the same batch, so we can go back to it if we find something we don't understand. Great question.
Professor Bhandari has a question. The white-looking rocks on Bennu, are they eukaryotic? Why Bennu has such a complex history? Is such a thing quite common for NEOs?
Yeah, great question. So the really super bright ones are probably eukaryotic. They're probably HED materials. And the current dynamical models for Bennu actually also predict it might be directly related to Rugu, and that on Rugu you find best way to answer this question is comparison, so bear with me. You find other boulders that appear to be ordinary chondrites, S-type asteroid material. So clearly there's been a dynamical banging around of material in the solar system that is being accumulated and collected by these two asteroids. And most likely, in our case, for Bennu, we predict at least two major lithologies based on different boulder types that we will bring back.
So, but was there something of similar kind seen in Raigu too?
Not, yes, there was exogenous materials, as spectroscopists call it, in Rugu as well, but that's not eukaryotic. It is hypothesized to be ordinary chondrite-like. So probably collisions happened multiple times with different kinds of compositional objects, which is statistically not that surprising.
So there's a question by Deepak Kumar Panda, and he asks if Bennu and Raigu are similar to CM type 2, type 2.1 to 2.3, what additional information will we get from this sample return?
So well, that's right. So the current predictions are CI or CM like, and one of the things that we need to do is to actually ground truth the spectroscopy that is predicting the composition of the two asteroids through the analysis of the sample. So that's going to be critical. In the case of Hayabusa, Itokawa was predicted to be equilibrated ordinary chondrite-like because it's an S-type asteroid, and the spectral class is reference to laboratory spectroscopy of meteorites. So that was proven correct, at least for Itokawa. So now we need to see through sample analysis, is it correct for Rugu and Bennu? And hopefully there'll be a few surprises as well, I hope. Of course, if it's CI-like, then there won't be any chondrules for me to work on, which I'll be disappointed.
Right, right, absolutely. Another question is, the spectral line in 2.7 and 3.3 of the MI are taken in lab of regolith material. If so, it may be for all the dust? May not be for all the dust.
No, so what we're looking at is the footprint of the spectrometer, so it's a large area. I don't remember exactly, so it's kind of a mixture of material. So when you get down to the actual sample level that's coming back, we may be able to distinguish different kinds of rock material, for sure. But overall, it may just give you the same kind of spectra, but in reality, it's a mixture to give you that to you.
So there are a few questions people have been asking about what analysis is planned for Bennu and Hayabusa, both samples. What are being planned in future?
That's great. So the analysis process, which I didn't go into in detail in this talk, because for OSIRIS-REx, we're still actually going through the process of finalizing our plans. And Hayabusa 2, of course, is now in the process of analyzing. We have two major areas, inorganic and organic chemistry. And in the case of OSIRIS-REx, we have a whole series of hypotheses that we will be testing through the analysis of the return materials. So first and foremost, the most important analysis is visual inspection, documenting what we see, taking images and movies. And then a certain percentage of material will actually basically CAT scan or CT and get three-dimensional images of the whole grains. Those that will go on to organic work, we won't do that with necessarily because that process could damage the samples. So the organic analysis will begin concurrently with the inorganic, with the goals obviously of looking at every kind of prebiotic compound we can possibly analyze. And both in situ and more destructive processes will be used in the sense that we'll be grinding up material. We'll also be making thin sections or polished butts of the rocks as a standard procedure to use on things like a nanosims as well, and electron microprobe, etc. So everything will have a basic characterization of the minimal amount of information we need in order to satisfy ourselves confidently that we know what the rock is before it goes to the next stage.
Right.
Because I'm a petrologist, and that to me is the most important thing, is what is the rock besides its compositional differences and, you know, isotopes.
Right. So Professor Bhandari is a bit confused why such a small asteroid like Bennu has all types of rocks, basalt, organics, and other type of rocks.
You know, I've asked myself that question many times. It's like, why does the universe, for some reason, send the most important meteorites that fall on Earth to India? I don't know. So it's a great question, you know? I really don't know the answer to it. It has to be this complex dynamical history that the solar system is recording through these rocks, and hopefully we will be able to read these books known as rocks and the pages known as minerals to understand that. It's a great question.
So Ashok Ambastaji is asking you, the composition is very different than that of the Earth soil. What about its age?
Ah, great question. The age, and you can even speak to this too, but the age of the material is either the geologic age with respect to the activity when the asteroid was a larger body and was actually geologically active in its interior, fluid moving around or thermal processes beginning to metamorphose it or heat it up, or material left from before that geologic activity occurred in the asteroid. And that's what give us the absolute date of the solar system, is objects such as calcium-rich, aluminum-rich inclusion, which is a structural component of chondrites. Chondrites are essentially sedimentary rocks. They're cosmic sedimentary rocks, they're accretionary rocks that are composed of different materials that formed at different time periods and different locations within the planet forming disk. At least that's the current party line.
So Professor Banerjee asks you, have you constrained whether organics are absent or present on Bennu?
Well, we know from the spectroscopy that they're there. We don't know what they are, but we have a signal that tells us that there are organics on the surface of Bennu. So now we get the sample back and we find out in more detail. If it's something like a CI chondrite, it'll be a very simple, you know, set of analysis that happen. If it's something like a CM chondrite, there'll be much more complex things there that we can do, because the aqueous alteration that makes a CI chondrite basically eliminates certain kinds of organics.
So Ranjan Gupta ji is asking you, did Hayabusa sample reveal anything remarkable in terms of porosity and composition?
Stay tuned. I can't answer that question yet.
Yes.
Stay tuned.
Was there deployment of magnet in sample collector and any possibility of it being magnetic?
No, we can't do that in the sample collector for OSIRIS-REx because our TAGSAM unit actually has articulating motors that move, and that would overprint potentially on any sort of magnetic signature we have, and et cetera. So we didn't go that route, no.
So looks like That's all? No, we have one more question. You
Okay.
said basaltic material, the bright materials on Bennu.
Hmm.
Please comment more on this. How the basaltic material can arrive on chondritic parent body?
Yeah, that's a great question. So this has been noticed for other bodies like Ceres, for example. We know we have meteorites, iron meteorites on the moon and on Mars. So it's an issue of cosmic events that occur that I would, in a sense, I'll say cosmic accident, but there are no accidents in the universe that allow material to move around. And once one object hits something else, you send it on a new course. You can break it up very easily depending on the mass of the two objects and the velocity. And it becomes a statistical game of what will be the next object hit by fragments of something else. And of course, that also depends on the size and the mass of the body being hit. The larger it is, the more gravity, etc. So it is not a surprise, but on a tiny little body like that, you know, it was a little bit of a surprise, I guess, to be honest.
Right.
Yeah.
I think it's the same answer for next question. Do different types of rocks on the surface suggest interasteroidal collision or multiple meteoroid fall?
Yes, they do. Yes. That's the hypothesis anyway.
So, one question from me: Is the parent body of this meteoroid, the size of this asteroid, been calculated already?
Ah, great question. Not really. So I say not really because some dynamicists like Bill Botke have hypothesized and worked on certain numerical simulations which require that you make an actual determination before you begin your calculations of what something might have been. But the real test is going to be from the sample analysis and the amount of alteration that has occurred, geologic alteration in the sample. That will allow us to predict the size of the original parent body to some level, because we'll need to know pressure as well. And we'll get that from the material.
I have a question.
Now I can see everybody. I didn't realize I was still sharing. I'm sorry.
Yes.
Yeah.
Yeah, it's been a fascinating talk. One curiosity question I have is one of the slides that you showed, wherein there was ejecta coming out. You said that you thought that they were stars, but they were not stars, but dust ejecting out. What's the kind of size of the dust? If they are heavy, what makes it what makes it eject?
Great question. Yeah. So the same thing happened on the Voyager probe when the plume outgassing was found on Io, the volcanoes. It was a nav camera that actually found them, and the scientists working on it changed the filter and said, "What's that?" So that's really what happened here. Is but they're not those stars. I don't know those stars. So it was an issue of simply re-looking at images that were taken. Now that stated, the particles range in size from unresolvable, so dust size, you just get a hint of something going on because it's flickering light, to an order of several centimeters big. And in some cases, the particles themselves actually, we hypothesize, are probably flat because we can see it in an image. 7 seconds later, you can't see it. 7 seconds later, you see it again. That stated, that we've had many large-scale explosions and lots of little, what I call popcorn explosions. And the actual hypothesis that we have tried to explore as to the cause remains a little bit elusive, because we had expected the closer we get to the asteroid, or the closer the asteroid gets to the sun, the more of these events would occur. But it wasn't linear. As the asteroid was moving away, even as it's rotating, there were some particle ejections that occurred even farther away. So it's a little bit, challenging. So we don't know. So it's a great challenge. But one of the ideas is just like in comets, internal forces pushing things, squeezing things. The other one is, of course, trapped water within the phyllosilicate sheets actually exploding because they're heating up. So it's a huge, it's a huge shock in some levels that we saw it. So it was great.
Thank you.
And it might happen on LUNAR, I'd like to point out, but we don't have the imaging capability on Hayabusa 2 and a navigation solution to have found it. So that's a difference. Because OSIRIS-REx literally orbits the asteroid when it was there. Hayabusa 2 spacecraft comes back and sits.
Thank you.
Thank you. Good question.
So looks like there are no more questions.
Oh, our director has a question.
Oh, yeah, he does.
It's so interesting, you know, to know at least not only just science, but that technological part of it also. I just wanted to know when the sample collector was open to collect the samples on the surface, how long you had the exposure of keeping it open for collecting the samples.
Right. So the entire movie you saw, I'd have to go back and double check my memory because there's so many things in it anymore, and our world has made me forget certain things. But I think the entire collection process, because we went in so deep into the surface of 48 centimeters, I think it was 12 seconds.
12 seconds.
Seconds. The entire collector is designed to collect within 6 seconds.
And then you pull it back and close it.
Yeah, then it just pulls back, and then the collector remains open until we finish our investigations and put it into the sample return capsule. So it wasn't very long. Neither spacecraft, Hayabusa 2 or OSIRIS-REx, was the collection process more than, you know, a 10 seconds, 15 seconds long. The difference between the two asteroid missions is in Hayabusa 2's case, they fired a tantalum bullet, so they can make regolith if they have to. They can make their own sample. OSIRIS-REx required there be sample there to begin with. So the engineering requirements are slightly different between the two.
Mm-hmm. Mm-hmm.
Which is
And
totally cool. Which is totally cool.
Oh, right, absolutely cool. But after collecting, you are leaving it open for quite long time just to see that things have been collected or not.
Just a few days. The whole process was just a few days total. So within 24 hours, we moved the arm to take a picture of it. And then within 48 hours, we decided to stow it. So within 72 hours after collecting, a sample was in the sample return capsule. It's pretty
So
quick.
do you expect any changes from pristine sample collection to the closing time, which would be 24 hours to 72 hours?
Great question. No, we discussed that, and we don't expect any change in the sample between collection and stowing, other than looking for any contamination from the thrusters. And both space missions have different kinds of thrusters. So in the case of Hayabusa 2, they have really powerful thrusters compared to ours. Ours are something like 16 newtons. They're not very big, but the Hayabusa 2 was it was much more than that, like 60 or something. So it was significantly different. That's a great question. As to anything happening over time, if I can use your question as a lead in to talk about another issue, which is equally as important, sort of getting to, which is the difference between the two missions on the return trip. In the case of Hayabusa 2, which brought back just 5 grams of material, 5 grams, which we can do a lot with, the sample return capsule is hermetically sealed because it's so small. So literally the team siphoned off gas from, or if there is gas, I can't tell you that, but gas that may be in there when the sample return capsule came back. In the case of OSIRIS-REx, we have a large sample return container that has to vent to the air for the pressure. So we actually are open to atmosphere, but we have a filter in the exchange process to catch anything that may be going in or out. So that we won't be able to do the same kind of experiment as Hayabusa 2 did on OSIRIS-REx.
Just to complete the story, Now, I understand that it will be something like 2 days of exposure before it is closed, or 3 days of exposure. Don't you expect any changes due to radiation, particularly charged particles on one side, and the electromagnetic radiation.
Yeah, so that's a fair enough question. For the material that's caught inside of the collector itself, no. We don't believe so. Anything that was on the outside that's stuck to the outside as we put in the collector, I'll let you know in a few years. We'll be able to compare. So it's a great question. Yeah. I see.
No, but what I saw was that you had small openings, right? On that circular ring.
Yeah, that's not open. Yeah, that's not actually open to the outside. There's a mylar cover on the inside, so it's not exposed directly to the outside. So that's an aluminum mesh, and inside the aluminum mesh is a see-through mylar material that actually holds a sample in there.
I see. And what is this material of which your collector is made of?
The TAGSAM head, what is it made of? It's aluminum AL998, I think, and then it's anodized on top of that. I'd have to go back and check the paper on that because I don't remember the exact details. But I think that captures most of it. And then the mesh itself is actually a stainless steel, I believe.
Okay, great. Thank you.
Yeah.
Durga, you have a question?
Please.
As I understand that the sample collector has impacted around 40 centimeters or beyond to the surface for collecting the sample. So using either the impact force or any other sensor, was there an estimate about the surface physical properties of the asteroid?
Yeah, that's a question I'm glad somebody asked about. We have been working on that at some level tirelessly since we stowed the sample. And we haven't finished the analysis of the data we have, the telemetry from the spacecraft, from the accelerators, from the TAGSAM itself, from the cameras, from the spectrometers. So we're still doing that, and the paper is in the process of being finalized to go into science, but every time we get ready to do it, we find we didn't do something else, and we have to do it. So typical science process.
Thank you.
Yeah. And if it's published, which I suspect it will be, there'll be something like 100 pages of supplemental material with it. So you can certainly find pretty much any variable you want and any calculation in there. Yeah.
Look forward to that.
Thank you.
Harold, there's one more question. Where were the distances from Bennu to near neighbors measured?
Not by our spacecraft, no.
So looks like we have come to an end. Any other questions? So let me thank again Professor.
I have
Harold.
one small question,
Oh, sure.
if there is time.
Yes,
This
sure.
size distribution of dust on Bennu, can it tell something about the exposure time of the surface?
Well, obviously we'll be measuring that when the sample comes back. So we'll be able to do that through sample analysis. But right now, the part of the issue is knowing the granular properties of the material and being able to understand the impact properties as well. And that's been kind of tricky.
But you must have done it on the surface by photographs, right? So what is the size distribution of material? That itself tells how long it has been there, I guess, if it is being crushed.
Well, right. So the size, I'd have to go look that up. I don't remember the details, but obviously it ranges from millimeter-sized particles to boulders the size of 11-story buildings. So there does seem to be some potential areas where boulders may have been literally falling apart in situ. So there's some work being done on that, but I don't know the details to answer the question. I'm sorry.
Okay, thank you very much.
Sure.
A fantastic talk and a fantastic experiment.
Thank you.
So Harold, do you think there will be another asteroid sample return mission in the near future?
No, not from the US or from Japan. Maybe another country like China. They have stated in an abstract that they are interested in doing it, and we won't know until it launches that it's going to happen, most likely, which is fine. But I don't hear any sort of chatter anywhere that I'm aware of that another nation is interested in doing that right now.
So when we have already targeted 2 CM type of asteroids, which do you think would be next good target for an asteroid?
Well, you know, we're going to go to the Trojans and to Psyche, so we'll have some data on those particular asteroids. But if I wanted to collect another sample, for me, I'd like to go somewhere where we can get, you know, like an unequilibrated ordinary chondrite or something that's going to be in the middle, because if it turns out to be that these 2 asteroids are CI or CM, then we have 2 ends of the spectrum, a completely metamorphosed and a completely aqueous or altered, nothing in between. So
you're not materialistic. I would expecting that you would say some metal-rich asteroid or
no, I want to see
minerals, very important minerals.
I want to see chondrules. I said if there's no chondrules in either of these samples when they come back, I'll be 60 years old by the time I'm finished, and I will retire.
True. Thank you so much, Harold, for such an interesting.
Thank you. It's been wonderful. I really appreciate the questions, the discussion, and the invitation, and the happiness of 75 years. That's wonderful. Thank you.
Thanks, Kuljit. Thanks, Kuljit, for conducting this very interesting question and answer session. Before we proceed to the last vote of thanks by our Dean, I would like to request our distinguished guests of today, Dr. Radhakrishnan and Dr. Somnath, if they have any questions or remarks after hearing this lecture. I think Dr. Radhakrishnan has left, if I am correct, but he has left a message. He says, superb start with a scholarly talk, best wishes. So that's his message. Dr. Somnath, if you would like to ask any question, or if you have a concluding remarks or your message for us.
No, thank you. I have to tell you a big thanks to you for giving this opportunity to listen to such a talk by Professor Harold. I'm really privileged to hear that. And also, my interests are not into the science of this, but I am really enthused by the way you developed that arm to collect the samples. Okay, because I am into mechanisms and those type of systems, which is very, very interesting to see the idea and really finally seeing that it is becoming successful. You know, finally it matters. The type of simulation that you have done, and the one lesson I understood, even if you do thousands of simulations, finally what you really meet at the site where you really do this will never be will not be in those simulations. They will be out of the bound of those simulations. So that lesson's always, it happens. Maybe you came out successful ultimately. I'm really hats off to your team for doing such a wonderful mission, and thanks for making us understand the complexities involved in that. We are very privileged to hear from you. All the best for organizing this talk, being part of our celebrations of PRL's 75th anniversary, which is coinciding with our countries. Thank you so much, and really honored.
Thank you very much, sir.
Dr.
Now I
Nandita,
request.
Dr. Nandita, Dr. Rajiv is also there. I see. He is logged in. We are not able to see him. Dr. Rajiv, are you there?
Yeah, actually my video was off. Thank you very much. Actually, it was a brilliant lecture by Professor Harold, and it was really illuminating. Though it's actually not exactly, I'm not working in that area, it's geology partly, but it was really illuminating and educative, and it was a great start for the PRL Ka Amrut Vyakhyaan. And thank you very much. Thank you very much.
Thanks a lot. Okay, now I pass on to Dr. Pallam Raju, Dean PRL, for giving vote of thanks. Dr. Pallam Raju, please.
Thank you, Nandita. It's indeed great, it's a pleasant duty to propose the vote of thanks for this inaugural PRL Amrut Vyakhyaan series. First and foremost, I would like to thank our distinguished speaker, Professor Harold Connolly, for this fascinating, exciting, and informative and illuminative talk describing the challenging mission, its execution to get the sample and its way back to this globe, and it's been a fascinating talk. And I also thank you for being part of our 75 years of celebration. And I would like to thank our beloved and respected Dr. K. Radhakrishnan, former Chairman ISRO and Secretary DOS, for gracing this occasion and for inaugurating this Vyakhyaan series, and for sharing his appreciation of and expectation from PRL, and all the dignitaries and participants who have joined, both via WebEx and YouTube links. I thank you all for your interest, participation, interactions that took place, especially, Dr. Somnath, Dr. Rajiv, Professor Bhandari, and all other senior colleagues. And I would like to thank place on record our contributions made by the PRL Amrut Vyakhyaan Committee for putting together this program. Before I close, I'm happy to announce that next week we'll have the Vyakhyaan by another distinguished speaker. He is Dr. S. Somnath, Director of Vikram Sarabhai Space Center, who is joining, who has been part of this first lecture as well. And this center is named after Professor Vikram Sarabhai, who is the founder of Physical Research Laboratory. And his birth anniversary falls on 12th August. So it's very apt that on 11th August, next Wednesday, 4 o'clock, Dr. Somnath will be sharing his experiences and advances made in terms of launch vehicles to reach the sky. So I look forward, it's all are welcome. I look forward to seeing all of you next week. And with this few, remarks, I would like to thank one and all. So this brings this today's event to a close. Take care and see you next week. Bye-bye.